For this lecture, we will discuss the situation in which you would like to compare the distributions of two populations. To do this, we usually use a measure of location. This is when we can assume that the shapes of the distributions are similar. If we knew that the two populations came from normal distributions, then we could use t-tests and compare population means. If we cannot make that assumption, then we will use median as the measure of location. The tests that we will use will be based on the type of samples we have. If these samples come from independent populations, then we use the Wilcoxon rank sum or the Mann-Whitney tests. If they come from dependent populations, then we use the sign or Wilcoxon signed rank test. Let's first discuss the independent tests. We will first look at the assumptions. For these tests to work, we need to assume at least that the data is ordinal. Most of the time it will probably be continuous. Also, we need to assume that the shapes of both distributions are similar in nature. Let's start with the Wilcoxon rank sum test. The Wilcoxon rank sum (WRS) test is used for comparison of two independent sample distributions. It is an alternative for the independent two-sample t-test. The test will be done based on the ranks of the data. Let's look at an example. Here is an example where we are comparing blood samples from two groups. These are two different groups, so the test that we should use is an independent test. We wish to compare the median MSCE for the two groups. The data from the study is on the next slide. Here is the data. Now the first thing that we should do with any data is plot it. Let's try a dot plot. Here is the dot plot. Recall that for these tests to work, we need the shapes of the distributions to be similar. So there are some questions that we should be thinking about at this point. Here are the questions that we should consider. Do the data come from normal distributions? Are the two distributions similar in shape? Is there any difference in the measure of center for the two samples? Here are the answers. Unfortunately, we can't say much about the distributions as the samples are too small, although there does not seem to be any clear lack of symmetry. Again, it is hard to say much with such small samples, although the white data seems to have longer tails. The plots suggest a difference with Native American values being larger on average. Let's take a look at the null hypothesis for this test. In this case, we should assume that we have two samples to compare, each with a certain sample size, not necessarily equal. We are testing the hypothesis that the distributions in population A is the same as B. Recall that we usually do this with measures of location, so this is really no different than testing equality of medians. What are the potential alternative hypotheses? The alternatives here are based on the direction of the median shift. Just as with most hypothesis tests, the alternatives could be greater than, less than, or not equal to. Let's visualize this for greater than. You can see from the illustration that for the null, the distributions are on top of each other. The alternative shows that the measure of center is shifted toward the high side. Now let's look at the test statistic. In order to find the test statistic, we first need to combine the two samples. Now we find the ranks of the combined sample. The test statistic then becomes the sum of the ranks of the data that come from the first sample. Once we get the test statistic, we need to find the p-value. Some people believe that ties should be thrown out. Others think that since a tie does not give weight to either side, so you should add 0.5 to the test statistic. The problem with adding in ties is that you cannot get an exact p-value, and with enough ties, could have a large effect on the outcome. We will throw out the ties. The distribution of the test statistic is not a typical distribution such as normal, chi-square, f, etc. That being said, we do have tables for certain combinations of sample size. We can use them to find the p-value for the test. How do we find the p-value? Here are the alternatives and how to calculate the p-value and build the rejection region. So now let's look at an overall procedure on how to do this test. Here is the procedure for the WRS test. Combine the groups and sort them into ascending order. Assign ranks to the combined groups. Find the test statistic WA by summing the ranks of group A. Determine the p-value. Now let's apply this to the blood sample example. Let's run the test with a not equal to alternative and a equals 0.05. We will use the Native American group as the first sample. First, let's determine the test statistic. By following the procedure, we can see that the test statistic is equal to 75. Now for the p-value. We find the p-value using a computer package. Now we can draw conclusions. Just like with most discrete type tests, we can approximate the WRS test with the z-test. If the sample sizes from both samples are greater than 10, then the approximation holds. In this case, we get the mean and standard deviation for the test statistic based on the equations on the slide. Now the test statistic is found based on the equation in the slide and follows a standard normal distribution. Here are the alternatives and how to calculate the p-value and build the rejection region. Let's do an example. This is a project where the metric of interest is the time between events. This type of variable usually does not come from a normal distribution. In this problem, we want to compare a new method to the old method. Let's first check for normality. Based on the normality tests, neither distribution is normal. Since neither distribution is normal, we will use a non-parametric test. Here that will be the WRS test. Since both sample sizes are bigger than 10, we will use the normal approximation. Here are the hypotheses. Since we would like to know if the new method takes less time than the old, we will use a less than alternative. Let's look at the calculations for the approximate method. Notice here that W is equal to 399. Now we find a p-value equal to 0.383. Let's draw conclusions. Since the 0.383 greater than 0.05, we fail to reject the null. There is not enough evidence to conclude that the median time for the new method is less than the median time for the old method. What would we get if we used the exact test? Here are the results of the exact test from Minitab. Notice Minitab calls it the Mann-Whitney test, yet they give you the WRS test statistic. Here we get a p-value of 0.3882. In both cases, we would fail to reject the null hypothesis. The p-value for the exact test is quite close to the approximate test. The approximate test is fine to use in this case. The Mann-Whitney M test yields the same results as the WRS test. The main difference is the test statistic. The test statistic U is the number of x, y pairs where x greater than y. We will also throw out all ties like we did for the WRS test. Let's look at some more details about U. The value for U indicates the relationship between x and y in the sample. A large value for the U statistic indicates that the values with treatment 2 tend to be larger than those from treatment 1. A small value for the U statistic indicates that the values with treatment 2 tend to be smaller than those from treatment 1. Let's look at an example. Consider the situation where an analyst would like to assess the usefulness of a new teaching method as compared to the current method. Suppose we are interested in testing if the new method is better than the traditional method. Let's test this hypothesis using the Mann-Whitney test. Notice that we need to assume that the subjects using each method are different. If not, then these samples would not be independent. Let's take a look at the hypotheses. Since we want to know if the new method is better than the traditional, we will use a greater than alternative. The data is on the next slide. Here is the data. Since the new method comes first in the hypotheses, we will use it as x for this problem. Now we first need to look at each of the x, y pairs. Here are each of the x, y pairs. You should be able to see from this that the number of pairs where x greater than y. Based on the pairs, 11 out of 12 yield neutrad. The value that we will use for U in this case is 11. Now how do we get the p-value? We do have tables for the null distribution for U. This is also not a traditional distribution. Luckily for us, we have computers to do this. This is the output for the Wilcoxon test function R. You need to make sure that you put the sample that comes in the hypothesis first in the call to the function first. So assuming that you created the two samples and called them new and trad, the call would be Wilcoxon test, new, old, alternative equals G. We can see that the results yield the p-value equals 0.057. Let's draw conclusions. Since the p-value is quite close to 0.05, it is difficult to draw on definitive conclusions. I would try to collect more data. If that can't be done, then you should err on the side of caution and choose fail to reject. Just as with the WRS test, if the sample sizes are large enough, we can use the normal to approximate the MW test. The main difference here is that the mean will be different. It is given in the slide. Let's redo example 2 with the MW test. Here are the calculations of the approximation. Notice that we get the exact same test statistic value in this case. We would fail to reject the null since 0.383 greater than 0.05. We get the same answer as when we used the Wilcoxon rank sum test. Now, how do we decide which one of these to use? The answer is that it really doesn't matter since they give you the same answer. It is going to depend on the software package. Minitab gives you the WRS test statistic but calls it the MW test. R gives you the MW test statistic but calls it the WRS test. Just like when we used the paired t-test instead of the two-sample t-test, we will need to use a different non-parametric test for dependent samples. Dependence usually occurs when the experimental unit does not change across samples. In this case, we will use either the sign test or the Wilcoxon signed rank WSR test. Let's first look at the sign test. We can use the sign test to test the equality of medians. To use this test, the data should be at least ordinal. The idea behind the test is the same as it was for the one sample case. We will adjust the observations so that we can count the number of pluses, minuses, and ties. We will find the differences between the respective paired observations and assess the pluses based on them. We determine the differences as seen on the screen. In order to label the differences, we will need to compare each one to 0. We label a difference a minus if D0. If D0, we define that observation as a plus. Finally, if D equals 0, we define that observation a tie. The test statistic T becomes the number of pluses. We label the observed value as T plus. Now let's look at the hypotheses. The null hypothesis will be that the difference in the medians is equal to 0. The possible alternatives will be greater than, less than, or not equal to. Now let's look at each of the tests and how to find the p-values. For the less than alternative, we will reject when the number of pluses are too small. This indicates that the median for population X is probably smaller than the median for population Y. We can calculate the p-value by calculating the probability given on the slide with the binomial distribution with n equals number of non-tied pairs and pi equals 0.50. For the greater than alternative, we will reject when the number of pluses are too big. This indicates that the median for population X is probably larger than the median for population Y. We can calculate the p-value by calculating the probability given on the slide with the binomial distribution with n equals number of non-tied pairs and pi equals 0.50. For the not equal to alternative, we will reject if the number of pluses are either too big or too small. We can calculate the p-value by calculating the probability given on the slide with the binomial distribution with n equals number of non-tied pairs and pi equals 0.50. Let's look at an example. Based on this example, this is a dependent situation. This is because it is the same intersection used for both method A and B. The number of accidents that occurred during that time period is the response. The data is on the next slide. Do the data provide sufficient evidence that a difference in the distributions of accident rates exists? Let's first take a look at the data. Here are the counts of the number of accidents in each group. Now let's look at the hypotheses. The hypotheses are included in the slide. Notice that the alternative was not equal to. Also, you should notice that I have method A first. It doesn't matter in this case what comes first. It only matters that the values for the one that is second should be subtracted from the values for the one that comes first. So in this case, we will subtract the values in group B from the values in group A. Let's take a look at the calculations. Notice that we have taken the differences in the AB column. You should also notice that we do have one tie. So there are 8 pluses, 3 minuses, and 1 tie. Now let's find the test statistic in p-value. The test statistic in this case is t plus equals 8. Now with a two-sided alternative, we get the p-value as given in the slide. Now if you wanted to run this test in Minitab, how would you do it? The sign test in Minitab is only set up for the one sample case. In order to make it do the paired case, we will use the differences as the observation and test for the median equals 0. You can see from the output on the slide that the p-value is the same as when we used the binomial test. Let's draw conclusions. Since 0.226 greater than 0.05, we fail to reject the null. There is not enough evidence to conclude that there is a difference in the median number of accidents based on the two types of traffic controls. Now let's talk about the WRS test. This test can be used for the paired situation as well as the one sample case. The WSR test is better to use than the sign test when the two distributions are continuous and symmetric. The technique is similar to the one sample case except the differences will be based on the data from both samples. Let's look at the absolute differences. To prepare the data for the Wilcoxon sign rank test, we need to transform the observations by using the absolute differences between the paired observations from each sample as seen in the slide. Again, the veil for X should be taken as the first group from the hypotheses. Now let's find the test statistic. Here is how we find the test statistic t+. Find the differences for each observation. Determine the ranks based on the d. Determine the value for re by adding the sign of d to each of the ranks. Now the test statistic becomes the sum of the ranks where the differences are positive. At this point, we will use the normal approximation to find the p-value. Here is the approximate test. Notice that this is a form of the z statistic. We will assume that the test statistic follows a standard normal distribution. Here are the alternatives and how to calculate the p-value and build the rejection region. Notice that for the less than alternative, we need to take the negative of the test statistic. Let's do an example. Here we will redo the traffic example, except this time we will use the WRS test. Here are the hypotheses in question. Notice that the alternative is not equal to and the first group is group A. Here is the table that show who we get the signed ranks. The signed ranks are the values in the ranks column that are in bold. Notice we remove the tie. Let's look at some details. The test statistic becomes the sum of the positive ranks, which is 51.5. Now we will use the approximation to get the p-value. Here are the calculations. The p-value becomes 0.110. How do we do this with Minitab? Again, we will need to use the differences since the test is set up only for the one sample case. You can see from the output that the p-value is the same as the one we got when we did it by hand. Let's draw conclusions. Since 0.110 greater than 0.05, we fail to reject the null. The sign test gave the same conclusion, although the p-value was higher at 0.226. Use the WSR test when both distributions seem to be continuous and symmetric, otherwise use the sign test.